Hello, and welcome everyone. This is MOOC 17, the Massive Open Online course for the University of Nicosia's Master's degree in Digital Currencies. I'm Andreas Antonopoulos, and I'll be answering your questions today. This session is a particularly big one. We have a lot of really important fundamental things to do. The fundamentals of cryptography, the hash function, mining, and some of the software that is involved in Bitcoin and other blockchain technologies. So I'm going to mostly focus on the questions today because the questions will allow us to illuminate many of the issues and many of the topics for today's presentation. So first of all, a quick sound check. Just let me know in the chat if you can hear and see me well, and I'll keep an eye on that. It's usually just a tiny bit delayed. And then we'll dive in directly into the questions. All right. The first question is about change. Why does the Bitcoin network give change back to the sender of a transaction? Why does it not transmit the exact amount in the first place? Asks Andreas. Swapan answers, blockchain transactions follow one of two models: unspent transaction output, or UTXO model, the UTXO, unspent transaction output model, or the account-based model. So the UTXO model is the one that's used in Bitcoin and Litecoin, Dash, and a bunch of other things that are closely related to Bitcoin, whereas Ethereum and many other EVM blockchains use the account-based model. This is a great answer by Swapan, right on the dot. So let's describe these two models. As Swapan says, the UTXO model is like spending cash. That means coins or paper notes, and getting change in return, while the account-based model is like a bank account where you do a debit and a credit for the specific amount you want. Now, if I have, let's say, a 20 euro note, and I go to a shop and I want to buy something that costs 3 euro, I can't divide the 20 euro. That's all I have. Maybe I have some other change in my pocket. I will have change money in different denominations. Maybe I'll have some euro coins, some 2 euro coins. Maybe I'll have a 10, a 5, a 20. And so from the collection of money that I have in different sizes, I need to find something that is either exactly or slightly more than the amount I want to pay. And based on whether it is exactly or something more than the amount I want to pay, I will then get change. So if I want to spend 3 euro, for example, to buy something, I could put together a 2 coin and a 1 coin and have exactly 3, or I could give, let's say, a 5 euro note and get 2 euro in change, or I could give a 20 and get 17 euro in change. You obviously know how to use money, so I don't need to explain it anymore, but that's how UTXO works. The account-based thing is more like you go to a shop and you pay with your debit card, and whatever amount you're paying, maybe it's 3 euro and 17 cents, that is exactly what's going to be reflected in your bank account. So any arbitrary amount can be charged against your balance, and your balance will go up or down based on the credits and debits in the account by the exact amount. So in Bitcoin, what we're working with is whole amounts, and these whole amounts are created and consumed by transactions. So it is a UTXO model, means that you have transaction outputs, TXOs, and you can spend the ones that have not been spent yet, which are the unspent transaction outputs. That's what you have in your wallet, if you like, what you have available to spend at any point in time in a UTXO model blockchain like Bitcoin is whatever transaction outputs in whatever specific units they are. You can't cut those transaction outputs in half. You can't divide them at all. You create a transaction that spends an entire UTXO or several UTXO, which is like taking out coins and notes from your wallet in order to make a payment. Now, if that amount is exactly what you want to pay, then your transaction will consume those as inputs and produce an output to the, let's say, the shop that is the exact amount that you want to spend. So let's say you have, and I'll go back to euro and compare it to coins. Let's say you have a 2 euro and a 1 euro available, and you want to spend 3 euro. So your transaction will reflect as its inputs the 2 euro and the 1 euro amount that you have available to you, and its output to the shop will be the 3 euro amount. That is then an indivisible amount that the shop has to spend. So unlike with physical money, these chunks are created in whatever amount they're created by a transaction, but once they're created, they can only be spent in whole. So when you create a 3 unit amount to the shop now has a 3 unit amount. It has to spend that entire thing. And therefore, if it wants to spend less than that, it has to make change. If it wants to spend more than that, it has to find some other outputs to put together. So let me know if you follow so far on this general concept. Transactions in Bitcoin, again, have two sides. They have the input side, and on the input side, we are consuming available outputs. Where did these come from? They came from previous transactions. So when you got paid by someone, the amount that you got paid as an output of a previous transaction is now available to you as a unit of spending in your wallet. And that's called an unspent transaction output. It's the output of the transaction that paid you. And now you can use it as an input to pay someone else. When you create a transaction that consumes that transaction will have an output. That output will be available to someone else to spend, and so on and so forth. Everything in Bitcoin is in the form of transaction outputs, these indivisible chunks of Bitcoin. Their value is measured in Satoshi, 100 millionths of a Bitcoin. That's the base unit of Bitcoin. And so you have whatever amount in Satoshi that output is worth based on how it was created by a previous transaction. That's what you have to spend. So if you have change, what you do in Bitcoin, let's say you wanted to spend, let's say, 3 Satoshi, and you have a 5 Satoshi output available to you to spend. So you construct a transaction that consumes the 5 Satoshi output that you have available to your address. And on the output side of the transaction, you have a 3 Satoshi output that goes to the shop. So that's to the address of the shop, 3 Satoshi. And then you've got 2 Satoshi left over. That 2 Satoshi, you're going to have another output to your address, to an address in your wallet as change. So you're essentially creating your own change. You're taking your 5 Satoshi input and you're splitting into 3 to the shop and 2 to an address that you own. That's the transaction. And then you'll have a 2 Satoshi output to spend sometime in the future, which was your change from this transaction. So let me know in the chat if you have any follow-up questions. I don't know how many people are on the live right now. I'm not seeing too much activity in the chat. So perhaps I'm looking at the wrong chat. You could make some noise in the chat. That would help me know if we have anyone in the live audience today. Or if I'm looking at entirely the wrong chat. All right, and Dimitrios, if you could please let me know either in the chat or on our private channel if I'm not seeing anything in the chat, so I don't know if I'm looking at the wrong thing. All right, our next question comes from Bradley. Bradley says, as Merkle trees are already utilized in Bitcoin, Ethereum, and Bitcoin forks, will we see it either formally or informally adopted as a standard for many other blockchain technologies as well? Merkle trees are used ubiquitously. Second, that is active. I am looking at the wrong chat, so I need to open the chat. Let's see. So Merkle trees are used ubiquitously, not just in blockchain technologies. They're used in databases, they're used in file systems, they're used in storage archives. They're used in a variety of places where what you need to do is create a summary of hashes or fingerprints for large data sets, where you need to be able to know if something belongs or does not belong in a set, if something exists or does not exist in a set. One of the most efficient ways to do that is to use Merkle trees. So whether they're standardized or not, you can implement Merkle trees in a variety of different ways. The exact implementation can vary. In fact, in Bitcoin, we have a number of different implementations, including tagged Merkle trees with tagged hashes. And in Ethereum, they use a slightly different variation. It's not a Merkle tree. It's a different structure that resembles a Merkle tree. Again, it is a tree of hashes, but it's slightly different than the one that is used in Bitcoin. And we see variations of this data structure. There isn't really a need to standardize these implementations, as a data structure is fairly common and broadly used. Okay, give me 1 second. I'm just going to try and reopen the chat because I have been unable to view any of the conversation here. Ah, there we go. All right, now I can actually see the chat, so I can interact a bit with people. So bear with me while I reorganize my screen a bit. Our next question comes from Angela. Angela asks, from an accountant's perspective, every debit needs a corresponding credit in the case of Coinbase transactions. I can see that there is no input to that transaction. Shouldn't there be an input or debit against the number of all remaining coins to be mined? What is the mechanism in place to record the newly generated coins and deduct them from the 21 million coins to ever be generated, which in turn give us the coins remaining to be mined? How is this reflected in the ledger? Angela, you're absolutely correct. In a traditional accounting-based double entry system, every credit must be accompanied by another debit. However, Bitcoin isn't a double entry accounting system. And so in the case of the Coinbase transaction, there's a bit of nuance there. The consensus rules keep a limit on the amount of coins that can be generated in the Coinbase transaction in each block. So right now, the maximum amount of new coins that can be in a Coinbase transaction is 6.25, 6.25 Bitcoin. That's the current block subsidy, and consensus rules enforce that. If you were to try to put, as a miner, if you were to try to mine a block, you can write in the Coinbase transaction anything you want. You could put 6.3 instead of 6.25. And who's going to notice? Everyone's going to notice. Your block will be invalid and will be rejected because it doesn't have the correct amount. And as a result, you will waste all the electricity mining to mine a block that is ultimately invalid because of that one difference. So one of the rules that is checked by every node is that the block subsidy does not exceed the current correct block subsidy based on the number of blocks that have elapsed, the number of halvings that have elapsed every 200,000 blocks, and therefore the correct block subsidy, which is 6.25. It's a fairly simple equation. You start with 50 every 200,000 blocks. You divide by 2 with an integer division. This is all calculated in satoshis as whole integers. And so you would start with 50 Bitcoin or 5 billion satoshis, and then divide by 2 for the next halving, and divide every 200,000 blocks, and you get to what the correct block subsidy should be at the very current moment. And if you see something different in the block reward, then you simply decline that block. Now, the other part of the question you asked is there any mechanism in place to record how many Bitcoin are left to mine? No, there isn't. By simply putting a limit on the amount of Bitcoin that can be issued in every block, and by having an adjustable difficulty that keeps those at 10 minutes, you can't issue more in the current period. And when a halving happens, that limit goes down and down and down until eventually, after whatever number of blocks in 140 years, you get down to 0 by continuously dividing. And then what you're left with, if you simply count the number of blocks that have elapsed at that point and the maximum subsidy that can exist in each block, the limit is less than 21 million. In fact, it's 20,999,999.999997, or something like that. So it's never 21 million. In fact, it's a bit less than 21 million. And that is not by a process of subtraction from 21 million. It's by a process of addition from 0. And that addition is always capped in every block, and that cap keeps getting lower with every halving, forcing the total issuance to follow this asymptotic curve where it approaches but never reaches 21 million. So if every block has a cap and that cap keeps going down, eventually you reach the maximum amount of coins because there is no more Bitcoin being issued. The 21 million limit is a side effect of the periodic issuance policy, meaning that we don't start with a number that is 21 million and then subtract how many coins we've issued. We have a fixed amount that's coming out every block, and by decreasing that amount, we end up below 21 million. Now, keep in mind, when we say below 21 million, it could be significantly below 21 million based on the simple fact that miners are not obligated to use the maximum block subsidy. So as I mentioned before, the consensus rule says that you cannot have more than 6.25 Bitcoin as a reward in your block. Well, you could put 4. If you put 4 in your Coinbase transaction, you'd get 4. There would be 2.25 Bitcoin that would never get issued. And as a result, you would reduce from the 21 million coins, immediately you would be taking off 2.25 coins that would never get issued. That doesn't happen often, but we have had occasions where blocks have had less than the maximum subsidy allowed, and those coins simply never get issued. So the best case scenario is 20,999,999,997, etc. But that's if every block has the maximum reward. But you can always reward yourself less. I don't know why you would do that, but you can. Yes, Eduardo mentioned in the chat, it's the halving happens every 210,000 blocks. Pardon me, Eduardo. That is correct. It's every 210,000. Did I say every 200,000? I misspoke. So thank you for that. Tatiana says, Zeno's paradox? Yes, pretty much. Except that unlike Zeno's paradox that continues to infinity, In the last halving, you go from 1 Satoshi to 0. You don't go to a half Satoshi because there is no such thing. This is done through binary division, which is basically a right shift operation on the binary integer number of Satoshis issued in the block subsidy function. So it's an integer, so you can't have a half Satoshi. And in fact, there was a bug in that code in the way the right shift was done so that it would happen one time too many. That bug has since been fixed, and it wouldn't actually be a bug until 140 years from now, but someone found it. Why would a miner choose to get a lesser reward, asks Jim. Great question, Jim. I have no idea why they would. That's throwing away money, but you know, in the early days, maybe someone did it just as an experiment. It wasn't worth anything. And I'm pretty sure that it's been done on chain, but I could be wrong. I know it can be done. Benjamin asks, what are the benefits and drawbacks of the UTXO model as opposed to the Ethereum account model? This is a very good question, Benjamin, and I'm sorry I'm doing it a bit out of sequence. I didn't see that. I had to keep refreshing my chat. It's not refreshing automatically. So some people say that the UTXO model is superior in some ways because it can be audited in real time, meaning that it is a fairly simple question to count how many UTXO exist now. You can just count them. They're in the database. They're discrete units. You can count how many exist and how many are unspent. And you know exactly what the current amount of unspent Bitcoin is, which gives you the total amount of Bitcoin that has been issued and not spent, which should be all of the Bitcoin that has been issued. So you should be able, you are able, in fact, in Bitcoin, and there's a command in the Bitcoin core software that allows you to do this. There was a whole controversy and conversation about this in the past, it was called Supply-gate because it's a scandal, as to the fact that within Bitcoin there is a straightforward command you can issue to audit the supply of currency, and that simply adds up all of the UTXO and tells you what that number is. And because it's in the reference client and it's a quick and easy command to run, it's a very easy database operation to just simply add up all of the values. Now, if you think about it, if you're looking at a bank account, and you think about it in terms of the real world. If you wanted to find out how much money a business had and they had it all in cash, well, it's very, very easy. How much is the total amount of money they have? Then you can simply add up all of the notes and count them. Whereas if you want to find out exactly how much money a business has in a bank account, but they have millions of bank accounts and they're moving money between them all the time, you have to be very careful about how you pick the exact point in time where you make that measurement. And in order to audit that measurement and make sure it's correct, you have to go back to when the account was opened, and then you have to add up all of the credits and all of the debits and make sure that they add up. So effectively, you have to do the equivalent of an accounting audit. Because you're not measuring whole units of currency, but it's simply a balance that goes up and down, in order to ensure that you have the correct balance, you have to say, well, how much money went in over time, how much money went out, and the final number should balance. You should balance the books. Now, that is not as easy to do in an account-based system. You have to do all of the sums. And so as a result, there are some ideas that it's actually less secure, less auditable. It's certainly less auditable in a public way than, say, Bitcoin. Paul has a follow-up question about inputs and outputs, and let's keep focused on that topic since we're still there. Paul asks, so if I have two input transactions of, say, 0.2345 and 0.29484, and I want to send 0.4, then I will take from those two inputs and give me back the change. You would take the entirety of both of those inputs. You have two inputs that are just over 0.2. You need to make a payment of 0.4. You don't have a 0.4 input to consume, so you need to consume both of the 0.2 outputs, UTXO, that you have, the unspent transaction outputs, and that is going to add up to more than the amount you want to pay, which is 0.4. It's going to add up to 0.51 something, so or 5.2 something. And so you're going to pay 0.4 to whoever you're trying to pay, and then you have a 0.12 something left over, which you want to give as change to yourself. There's an interesting thing here, because the way it works, there's also the consideration of minor fees. And fees are whatever change you leave on the table. Just like in a restaurant, if you make a payment and you take your change, and then when you get your change back, you only take some of it and you leave some on the table, that's the tip. So similarly, minor fees, transaction fees, are not explicit in the transaction. They're whatever left after you take the change. So let's say you have 0.29, 0.23, you pay 0.4 to someone, and then you take 0.1 change. Well, the left and right side don't add up the same. There's actually a 0.02 something left over. That would be your transaction fee. It's not in the transaction. If you look for it, there's no output that belongs to the miner that you paid to the address of a miner. It's simply money that was consumed as inputs in a transaction, but wasn't paid out to the outputs. That's kind of left over from consuming those inputs. Where does that money show up? It shows up in the Coinbase transaction. So the Coinbase transaction for that block would be, the miner would pay themselves 6.252311, for example. They'd add the fee to the reward of 6.25. So when you look at the Coinbase transaction, it's never 6.25 exactly unless it's an empty block. It's 6.25 something, or 6.26, or 6.3 if there's a lot of fees. If you look at how much more than 6.25 it is, and you went through the effort, which you can do with a script, for example, or even manually if you want to do this, and you add up all of the outputs and all of the inputs in all of the transactions in that block, and you see how much money is left over, all of those fees, those will be the amount above the 6.25 reward. The excess reward that the miner is paying themselves is basically the transaction fees they're collecting from all of those transactions. The transaction fees are not in the transaction. They're the leftover amount from the inputs that were consumed but not paid as outputs. And all of those leftovers added together become an output in the Coinbase reward to the miner. If there is no leftovers, there's no transaction fee. You're trying to do a transaction with zero fee. It will be broadcast. It's still a valid transaction. Most nodes would reject a zero fee transaction. They have a minimum fee requirement. So you wouldn't propagate it very much. Even if you did propagate it, it would sit in the mempool of the nodes that you propagated in, and miners would not pick it up because it doesn't have enough fee to reward them. So you can create zero fee transactions. They're just not going to get mined by anyone. They're just going to sit around not getting mined. Aaron asks, so is the change reissued or is it the separate transaction in the Coinbase? The change is in the transaction you create change back to yourself. So you take the inputs you want to spend, you make one output to the shop, and then you make another output to yourself, which contains the change. So it's an output that you create in your own transaction. When you're making the payment, you're also in that same transaction putting an output that contains the change. That output is payable to an address you own. Now keep in mind, there's nothing special about a change address. Let's again get into this a bit more detail. If you look at a transaction and you see it has two inputs and two outputs, you have no way of knowing, okay, you see it has two outputs. Is one of those outputs a payment and the other one change? They could be payments. Both of the outputs could be payments. You could be paying two different people, or even you could be making two outputs to pay the same person. Or one of the outputs could be a payment, the other one could be change. There's nothing magical about a change output. Maybe the first output is the change and the second output is the payment. Maybe the big output is the change and the small output is the payment. Maybe the big output is the payment and the small output is the change. You can't tell. A transaction can have 100 inputs and 100 outputs. Are there any change outputs in there? I don't know. There's nothing magical about a change output. A change output is simply from the perspective of you creating the transaction. One of the outputs of the transaction you created doesn't pay someone else, but simply pays an address in your own wallet so that you get that money back when that transaction is confirmed. And it doesn't go to anyone else. But if you look at that output, if someone else is looking at that output and doesn't know that that address belongs to you, they can't tell that that output is a change output. They just see an output with a payment to a Bitcoin address for some amount. They don't know if that's change or if it's you paying a shop. And some more questions about the construction of transactions with inputs and outputs. Paul Winnick with another great question. And I see somebody else wanted the answer to this. So let's continue on that thread. This is good stuff. If I had multiple input transactions of many small BTC amounts, how does it choose which of those to use to send the 0.4? This is a really important question. So this whole area is basically what's called the wallet Utxo selection algorithm. So your wallet chooses which outputs to use. So if you go into a shop and you open your wallet and you look inside and there's a whole bunch of coins and a whole bunch of paper notes and you need to make a specific amount, if you want to be slick about it, you want to make exact change to make it easier for everyone. Maybe you do. Or maybe you have some other plans in the future and you want to break bigger money and make some smaller change so you can pay for the bus as soon as you exit the shop. So there may be all kinds of different strategies in your head which have to do with you managing the chunks of money you have in your wallet. Well, your software wallet in Bitcoin is doing the same thing. It's pursuing a strategy, not just for this transaction, but also for past and future transactions. So it will look at what UTXO it has available to it. Perhaps it looks at the mempool and sees that fees are pretty low right now, so you can make a bigger transaction. So maybe you want to consolidate a lot of loose change. This is like that annoying person in the line in the supermarket in front of you who, in order to buy something expensive, pours out a bucket of pennies onto the counter, and both the cashier and the person start counting pennies, and it takes 10 minutes. What are they trying to do? They're trying to consolidate all of the loose change they have into a bigger amount, right? To pay for something. That's their strategy at that moment. both exchanges and individuals do this on Bitcoin, on the Bitcoin blockchain, with a type of transaction we call a consolidation or aggregation transaction. And this, you'll see these transactions every now and then. They're transactions that have maybe dozens or even hundreds of inputs and one output, or a few outputs. And you're taking all of these little amounts, 0.001, 0.002, 0.003 Bitcoin on the input side, and you're essentially collecting them all together into one big UTXO. Why would you do that? Because you can only do that economically, profitably, sensibly, when the fees are low, when the utilization of the blockchain is low, and therefore you can do a big transaction with lots of bytes. Lots of inputs means big transaction in size, means more fees that you have to pay. So if the fee rate per byte is low, you can afford to do a bigger transaction. So this is maybe a good opportunity. And I've done this myself. I look at the mempool, it's, midnight on a Tuesday at a time when there's no price action. The mempool is empty. Fees are 1 Satoshi per byte. Great. This is a good time for me to consolidate a whole bunch of little change I have into a bigger UTXO that's more useful to me, that I can then later spend, let's say when the fees are more expensive. So that's exactly what you would do. You would use that opportunity. So your wallet is thinking about these things. Your wallet is going to pursue some strategy. Some wallets are sophisticated, other wallets are not sophisticated. Wallets can also, and this is very important, consider other aspects, not just fees and transaction size. One very important consideration is privacy. So if you have a bunch of outputs, those outputs may not belong to the same Bitcoin address. You may be using many different addresses, and you may have UTXO available to you from many different addresses. Now, you can use all of those in a single transaction, but guess what happens? When you use a single transaction that spends 3-4 inputs from 3 or 4 different addresses, you are effectively telling the world all of these addresses belong to a single controlling entity. Because they will see them merged in a single transaction, and presumably that transaction has applied signatures from a single entity, they can assume that that transaction is likely indicating that all of those addresses were owned or controlled by the same entity. And they can then go back and correlate all of the other transactions that have happened using those addresses. And if you keep doing this, eventually all of your addresses are going to be correlated with each other. So if your wallet has a, call it dumb strategy when it comes to privacy, it can actually reduce your privacy by consolidating UTXO from different addresses and merging them together. Another consideration, you can spend UTXO that hasn't confirmed yet. And there's a variety of reasons why your wallet might try to do that. One of the reasons is to bump the fee using a technique called child pays for parent, where you put a bigger fee in the second transaction so that it not only confirms that one, but also confirms the previous one that is still waiting. So you can actually spend unconfirmed transaction outputs, but your transaction won't go through until both the parent and the child are confirmed. So that's another strategy your wallet might think. This is complicated stuff. The wallets have to be quite sophisticated as to how they pick UTXO, what size of change they create, so as not to leave you with too many small fragments. Some fragments so small effectively become unspendable. It will cost more in fees to spend them than they're worth, and therefore those are called dust. Dust outputs are outputs that are not economically spendable because the fee is more than the amount. All right, let's see what other questions we have. Yes, and to clarify, Alex asks, does using more UTXOs increase the byte size of the transaction and therefore mean that you might have to increase the fees to get a better Satoshi to kilobyte ratio and incentivize the miners to include it? Absolutely, yes. In fact, in a transaction, inputs carry a lot more weight than outputs. It is cheaper to make a 4 output, 1 input transaction than to make a 4 input, 1 output transaction. And that's because the output has an address and an amount. The input has a transaction reference, a signature, which is long, 30 to 40 bytes, depending on how you count it. And therefore, and if it's a complex script, the signature and script could be very long. And so, as a result, the inputs are going to affect the size of your transaction more than the outputs. This is one of the reasons that segregated witness produced a discount for signatures. Michael asks, so the change output is not something compulsory? No, you don't have to have change. If you don't have change, what happens? You're effectively giving it all to the miner. If there is any leftover amount, whatever change you don't take becomes a fee. And if you're so good that you make the amount exactly what you want to pay and the fee, then there is no change. Change is 0, so there is no output. Maybe you're lucky your output is just enough to pay the fees and the amount you're trying to pay. It's not compulsory to have change outputs, and in fact, as I said before, change outputs are indistinguishable. They're just outputs. There's nothing special for them. Do all wallets conform to using the same algorithm, or some wallets are better than others at this job? Absolutely not. All wallets are not the same. In fact, there are significant differences. There are very, very dumb, bad wallets that have very poor algorithms, especially when it comes to privacy, for how they handle outputs and output selection for constructing transactions. And there are wallets that are very, very good at this. Generally, privacy-focused wallets tend to be very, very good and very careful with output selection. And ones that are not so much focused on privacy are less good at that aspect. Maybe, and some wallets are so bad, they're bad at the fee management too. The quality of wallets spans a very big range. Bemke asks, is there a dust collection plan? Oh, well, the dust collection plan is if in the future the capacity of the network increases and the value of the dust also increases, basically the Bitcoin price goes up so that the dust is worth more, but there's enough capacity in the network that you can do transactions at a very low fee, then it's likely at some point that your dust becomes economically viable again. And this is one of the main reasons why you'll never see agreement to simply destroy dust. There have been a lot of proposals. People say, why do we have this hanging around? It's filling up a database with all of these UTXOs that are effectively unspendable. And the answer is they're unspendable today. But one, you don't know what's going to happen in the future. Maybe 100 Satoshis is worth a lot of money, and maybe the capacity of the network in the future is such that the fees are less than 100 Satoshis. Maybe they're just 1 Satoshi. So if it's a 1% fee to spend 100 Satoshis, then it's worth it. So it's economically viable again sometime in the future. That's reason number one. Reason number two is it's theft. It's unethical to invalidate people's money. Something that the prime ministers and presidents of many countries have ignored when they do things like demonetization, when they declare one day that these bills are no longer valid. So it's unethical and it's considered theft by many people. All right, so what we're going to do is we're going to shift gears a bit and talk about cryptography, transaction verification, generating a public key, digital signatures, and the like, all of which are topics that we need to cover next. I think now is a good time. Let me take a quick look at the time. Yes, very good. My document font is like this big, and then the clock at the top of my screen is this big, so I need my glasses to see it. Aging is fun. All right. Let's talk about generating a public key. First, let's talk about generation of keys. And this is a topic that people find very difficult to understand and very confusing. We'll go from there, then we'll talk about private keys, then public keys, then signatures, and gradually build up the concept. That's the other big chunk of topics we have for today. And thank you, Jim, for giving me that prompt so we can start talking about that. James asks, a private key is simple. I don't know if that's the same James and the Jim who suggested we shift gears. Anyway, James asks, a private key is simply a random value between 0 and 2 to the 256. Now, James says it's a random binary value, but it's just a number. It's important to understand in all of these things we're talking about, a number is a number. Whether you express it in binary, whether you encode it in binary, whether you encode it in octal, decimal, hexadecimal, base 64, or whatever else, or even mnemonic words like the seed phrase of your wallet. Again, all of these things are simply numbers. So in computer science, one of the things that's very difficult to understand is that ultimately all information is numbers, and all numbers can be represented in any kind of encoding or base number system you want. A private key is simply a number, and it's a number between 0 and 9 with 76, sorry, a number between 0 and 9999999 times in a row, approximately. So that's a number that is 10 to the power of 77, or precisely 2 to the power of 256. That's basically a 256-bit number in binary. It's an integer, meaning it doesn't have a decimal point. It's a whole number. 256 binary digits long, which in decimal corresponds to 10 with 76 zeros or 77 nines in a row. Whichever way you want to look at it. And it's not exactly, so the decimal representation isn't exactly that, but for shorthand, we're talking enormous numbers. So a private key is simply a number. Now, if you think about it in a different way, if you were to create a number line, and that number line started at 0, and it was 0, 1, 2, 3, 4, 5, and it just kept going. And this, because this is a very, very long number, the end of that number is at the other end of the universe, and even longer. It's a massive, massive number, so you can't actually visualize it. There's no physical equivalent. But let's say you have a number line like that. Selecting a private key is a bit like throwing a dart somewhere on that number line and landing on a specific number, anywhere from one end to the other, and you just pick one at random somewhere in that range. It doesn't matter which one you pick. So how does your wallet generate a private key? It generates a private key, and this is the same mechanism by which it generates a mnemonic phrase or seed phrase, which again is a 256-bit number. The way it does so is by essentially pick any number between 0 and 999999977 times. And it does so with a system called a random number generator. Now, depending on what your wallet is running on, what type of hardware it's running on, it will have a variety of random number generators available to it. Because what we're doing here involves money and cryptography, we want a good random number generator. And so good random number generators are called cryptographically secure pseudo-random number generators, or they're called true random number generators. TRNG, true random number generators, or CSPRNG, cryptographically secure pseudo-random number generators. A pseudo-random number generator is not a truly random number because it doesn't use a random physical process, but it's simply picking from a sequence of numbers generated in such a way that you can't predict the sequence. So it is pseudo-random. It's not actually random, but it is effectively secure for cryptographic purposes. Most operating systems offer a cryptographically secure random number, pseudo-random number generator. Some devices, for example, hardware wallets, have built in a true random number generator, which is a hardware device that uses elements of physics, for example, noise caused by cosmic radiation in a feedback loop on the chip, in order to produce a true random number that's based on the randomness of the environment. For example, cosmic radiation. So a hardware wallet would generate your random number using a physical process. A computer may have something similar on it. Modern computers all do. Older computers don't, but in any case, it would use a cryptographically secure pseudo-random number generator. And it would pick a number in that range. Now that's your private key. Think of it as a PIN number, only it's a 77 digits PIN number. And once you've picked it, you know that no one else could guess it, simply because there are so many possibilities that even if billions of people were guessing billions of numbers, billions of times per second for billions of years, you would still not get this result. By the way, you may have noticed I said billion, I think, 4 times. And a billion is 10 to the 9. And if you multiply that 4 times, you still do not get 77. In fact, you fall very, very, very far short of it. So that's how big these numbers are. From that private key, you now produce a public key using a one-way function. And this function is the elliptic curve multiplication mapping function. It's not actually multiplication. It's not multiplication because we're not talking about integers where you multiply them with each other. It's a transformation. We use the word multiplication to describe an operator that behaves similarly to the multiplication operator that we use with integers. In this case, we're multiplying a number, which is the private key, small k, if you like, times a point on the curve called the generator point, capital G. Now, how do you multiply a number with a point? Well, in the elliptic curve domain, that is a transformation that involves point addition k times. So it's actually not k times g, it's g plus g plus g plus g k times. And that produces your public key. Every time you add 2 points on the elliptic curve, you jump from one to another, to another, to another. You're jumping all over the elliptic curve. One way to describe this in terms of transformation, if you like, which I like as an idea, I think it helps with the visualization, is think of you have a pool table, a billiards table, and your generator point, G, is a ball in a fixed position. And to Benjamin's point, the generator point is the same used by everyone generating their keys. Everybody uses the same point G. It's not random. It's a specific point. It has specific coordinates defined as specific coordinate XY numbers. It is part of the specification of the SEC P256K1 curve that is used in Bitcoin. And every curve within its specification, it's the secret number, not the secret, the known numbers that make the recipe of that curve, has a generator point which is defined as a specific point. It doesn't matter where it is, but everybody uses the same generator point, so you can repeat this process with a private key in any wallet. Now, once you, so back to the example. Let's say the point is a ball on the pool table, and your private key is the angle and force with which you hit that ball to make it go around the pool table. And you hit it, and every time when you hit it, it does this transformation where it bounces off the edges of the pool table, and it bounces all around. Now imagine that you hit it so hard that it bounces 1,000,000 times off the edges of the table, and then it stops at a specific point. The point where it started is G. Everybody starts from the same point. Like when you put the white ball on the specific point on the table that is marked, everybody starts from that point. But depending on how hard you hit it and the exact angle you hit it with, it's going to end up after 1,000,000,000 bounces somewhere. Where it ends up, if you were to see where it ended up, that's the public key. That is a point. You can do the XY coordinates on the billiard table. Can you figure out where you hit it or how hard you hit it? Can you figure out the private key? Well, you can't. You can't because arriving at that point, it could have arrived from any angle, and it could have bounced off any part of the table, and it's now bounced 1,000,000,000 times. You can't trace its path backwards. So that is a function that effectively is a one-way function. If you see where the ball ended up, you don't know how it was started, or even where it was started. And so that is a one-way function because it's very easy to make the ball go there. And every time you hit it, as long as you hit it the exact same angle and velocity, which is your private key, that's the secret in this case, it will always end up in the exact same point. But if you know the point it ends up in, you can't work backwards and figure out the private key. And so that is a physical example of the multiplication or transformation that occurs on an elliptic curve. In the case of an elliptic curve, every point generated by that multiplication function is also a point on the elliptic curve, which means it fulfills the elliptic curve formula, x squared, I think it's plus x minus 7 or something like that. I don't remember the exact formula for the elliptic curve of Bitcoin. And so every point is a point on the curve, but if you know the point of the public key and you know the point of the generator where it started, you still can't figure out how many times it's bounced around the elliptic curve, which is the private key that you started with. So you can't work backwards. You can go forwards from the generator point and the private key. You can derive the public key easily, quickly, in a matter of seconds. It's a simple process on any computer, and the inverse is impossible. All right, so think about that for a second. Tell me if you have any follow-up questions. Now, let's talk about the public key. The public key is a point on the elliptic curve that's characterized by coordinates x and y. And because the actual formula of the elliptic curve is known, every x produces only two possible values for y. So you can actually encode a public key just with the x coordinate. You don't need the y coordinate because you have the function. You can work out the y from the elliptic curve function, x cubed plus x plus 7 or something like that. Now, every x results in two possible values, y and minus y, the two mirror images on the elliptic curve. And so we can basically call the public key simply the x coordinate. And that means that the public key is effectively a number, and it's a number that is 256 bits long also. So you can store that as the 256-bit x value of the public key. So now you have two numbers. You have the private key and you have the public key. And you can easily generate the public key, which is a very big number, from the private key, which is a very big number, but you can't go the other way. Now, one second. So what is the point of all of this? The point is this. The point is that while you can't derive the private key from the public key, you can verify a digital signature made with the private key. You can verify it with the public key. So if your public key is known to someone, and in fact known to everyone when you make a transaction, then that signature allows you to verify that in fact you had the private key that generated this. So anyone can verify that a signature is correct by looking at the message you signed, which is the transaction or part of the transaction, and your public key and the signature, and verify that that signature is correct. And they can effectively know that you have the private key, that you generated the signature with the private key, even though they don't know what the private key is. So this mathematical relationship between private and public key can be essentially reflected in the signature in such a way that you can generate signatures with the private key, other people can verify signatures with the public key, but your private key remains private. This allows you to prove that the transaction was signed by you. So a couple more questions that come up with this. Philip asks, is the digital signature included in the transaction? Or how is it otherwise propagated? And how can the nodes verify the digital signature? The digital signature is included in the transaction. It is included in the input. In a traditional transaction, it is included in the input. In a segregated witness transaction, it is carried in the witness part, which is separate from the transaction, but is propagated in the block in a Merkle tree called the witness Merkle tree. But bottom line, the digital signature is sent with the transaction. So you put a digital signature on every input. Now, back to the previous conversation, remember we had several inputs we wanted to spend. Now, these inputs that we want to spend, we have to prove we want to spend them by signing those inputs. So every input contains a signature, and that signature unlocks that input, allowing it to be spent by the transaction. So the signatures go with the inputs. Now, as I mentioned before, a transaction could spend inputs that belong to many different addresses. So if a transaction is signing inputs with different addresses, then that means different private keys are signing the different inputs. But someone verifying it will look at the signature, will look at the address or public key that owned that output that you just signed, and we'll be able to use that to verify that you in fact control the private key. All right, so I'm going to talk a bit now about the Bitcoin software, specifically Bitcoin Core, and describe how that works so that we can move on to that topic a bit, unless there are any more questions that are follow-ups regarding public-private key. Quick answer of Konstantinos: can a tangent interject with the curve in more than 1 point? No. Or rather, if it does interject in the elliptic curve in more than 1 point, then that is the y minus y mirror of the public key. That's why the public key has one x value but can have two possible y values, y and minus y. That's because the tangent interjects on a mirrored point of the curve. So if the curve is like this, that line cuts y and minus y. And that's why some x's can have, well, all x's can have a y and minus y side. All right. So Bitcoin Core. Now, you've heard me talk about consensus rules, validation, signature verification, sending and receiving transactions and blocks, verifying the amounts within. Who's doing all of this? Who's doing all of this is the client software or node software. And that node software is running on perhaps your computer. Now, I run a Bitcoin node on a little PC I have. In fact, I run several. But one of the easiest ways to do it is you can run a Bitcoin node on a Raspberry Pi. You can run it on very, very small hardware. And there's in fact a number of software distributions like Raspberry and Umbrel and others that allow you to easily install, run, and manage your own Bitcoin node on a simple Raspberry Pi. In order to have a full copy of the Bitcoin blockchain, you're going to need a big hard drive, which you can connect externally to your Raspberry Pi. And when I say big, not really that big. It's about 350 gigs. And to give yourself room to grow and run other applications, 1 terabyte or 2 terabyte disk is more than enough. And nowadays, you can easily get that inexpensively as a USB disk or an embedded PCI memory disk flash drive. So that machine runs software. It runs usually a Linux-based operating system, or it could be a Windows-based operating system. And then on top of that, you run an application. And that application is the Bitcoin node software. Now, 90% or more of the nodes on the Bitcoin network run Bitcoin Core. Bitcoin Core is the name of a specific software project, which is the descendant, if you like, the grandchild of Satoshi's own code called Bitcoin. So when Satoshi wrote the software to run the Bitcoin network, it was called Bitcoin. Specifically, it was called Bitcoin Qt because it had a graphical user interface based on the Qt library. It's a library for making graphical user interfaces. So Bitcoin, Bitcoin Qt, Bitcoin Core all really describe the same thing. It's a piece of software that either runs with a graphical user interface or it runs on the command line in a headless server environment without a screen, without a keyboard, accessible through the command line. and it communicates over the network with other copies of Bitcoin Core or other copies of other software that speak the Bitcoin protocol, and does all of these functions. Now, Bitcoin Core has changed a lot since Satoshi wrote the first version. It got renamed from Bitcoin to Bitcoin Core just to describe that this was one implementation. It's called the reference client because Bitcoin does not have a formal specification of the protocol. The specification of the protocol is effectively written in C++ is Bitcoin Core. So if you want to find out how Bitcoin works, you read the source code. That is the definitive answer on how Bitcoin works, and you read the reference implementation of Bitcoin Core. It runs on tens of thousands of computers around the world. Estimates vary between 50 and 75,000 computers around the world run some version of either Bitcoin Core or other software that's compatible. Probably the most well-known software that's compatible is BTCD, which is an implementation of the Bitcoin node software in the Go programming language. So Bitcoin Core is C++, BTCD is Go, and there's a few others written that. So you can run a Bitcoin node in a variety of software languages, programming languages. You can write your own if it's a very difficult task. And it requires a significant amount of maintenance because you have to keep up with bugs and new things that change over time. As long as it follows the Bitcoin protocol and is compatible with the Bitcoin protocol, it will follow the consensus rules in lockstep with every other implementation. It will talk to other implementations, and you can run Bitcoin Core or BTCD or LibBitcoin or one of the others. And so Daniel has a question about that and says, I'm wondering about vulnerabilities through Bitcoin Core updates. If all nodes have to keep their Bitcoin Core software up to date and all have to download it from somewhere, is that not a centralized single point of failure if someone is able to organize a malicious hack of the Bitcoin Core code that implemented different rules when nodes went to download it? I suppose the answer is that all nodes update at different times, so it would be easily spotted. But wondering about it seems a point of weakness. This is really great stuff, Daniel. Very insightful question. So first of all, there is not just one place you can download Bitcoin Core. And the source code for Bitcoin Core is distributed using the Git protocol for source code distribution. It exists on GitHub as one of the places, but you can have your own copy. I have my own copy, which I synchronize with other repositories to keep up to date as changes happen. So you can make your own copy of Bitcoin Core by compiling it from the source code, from the C++ source code. You can download the binary, the executable, directly. Now, how do you know that executable is the correct executable? There's a couple of ways to know. So there's an entire process that is involved in Bitcoin Core development to ensure that you know you're downloading the correct software and that that software hasn't been tampered with, and it corresponds to the specific source code of a specific version of the Bitcoin Core software as it was compiled. A couple of different things. One, there are signatures, digital signatures, both in the commits and in the releases of Bitcoin Core. So you, if you want to go through the process, you can verify the digital signatures to ensure that you have a copy of the source code or a copy of the released binary that has been properly signed by the maintainers who publish their PGP public keys, and you can verify their digital signatures. So it's signed by maintainers. Therefore, if you just see an executable that says it's Bitcoin Core, you don't trust that. You have to check the checksum on the software and verify both the fingerprint and a PGP signature on that fingerprint to ensure that it is the correct thing. Now, there's another interesting process that goes into this called a deterministic build, which is a mechanism by which you can replicate the exact same set of tools to build the source code so that the resulting binary is bit for bit, byte by byte, exactly identical to the binaries that anyone else would build, and therefore you'll get the same checksum, and you can verify it against the same digital signature as the maintainers. This deterministic build process can be executed on your own machine and is executed, of course, to build the original releases. So you end up with a binary file, let's say a Windows executable or a Linux executable, that is identical to the one the maintainers themselves built. And in fact, that's simultaneously built in hundreds of different places around the internet, all of which should arrive at the exact same binary, get the exact same checksum, look at that checksum in the list of signed checksums, and find the digital signatures of the maintainers, verifying that that is the correct release. And they can also verify the source code and produce the same build on their own to verify that process. So all of this stuff is done as a process to ensure that when you download the software, you know you're running the software and it hasn't had some malicious thing introduced. Of course, the software engineers who work on Bitcoin Core could theoretically introduce malicious code in the source code. The defense against that is the fact that source code additions to Bitcoin Core are reviewed by hundreds, thousands of people, really, and they go through a lot of review and testing before they're introduced. Finally, as you noted, people don't all update the software at the same time. In Bitcoin, a conservative design principle is that you should not be forced to update your software unless you want to use new features or protect yourself against vulnerabilities or security problems. And you don't have to update your software in order to remain consistent with the consensus rules, meaning that it is very rare that in the Bitcoin system you will see a rule change that is not backwards compatible. There have been a couple of instances where there have been rule changes or software changes that caused a backwards incompatible change. One happened in 2010 when a bug in the source code generated a block with 184 billion Bitcoin in it, which is obviously more than 21 million and shouldn't have happened. As a result, the code was changed, the bug was fixed, the blockchain was rolled back, that block was erased, and the blockchain was rebuilt from that block to erase that transaction. All of the other transactions got replayed. So no change in anything except for that mistake never happened as far as the blockchain is concerned. There was another bug in April of 2013, if I remember correctly, where two different versions, where some people updated and some people didn't. Some of the people who updated to version 0.8 of Bitcoin ended up producing blocks that could not be validated by people who had 0.7 version of Bitcoin because of a change in the underlying database format, and that change having a built-in limitation that wasn't noticed at that time. That also caused the chain to fork for 26 blocks until a new version. Everybody reverted back to 0.7 in order to fix that. And then the blockchain rolled all of the transactions again, and you won't see any traces of it in the blockchain now. It's as if those 26 blocks didn't happen. The transactions happened, they just happened again. And so everything got recorded normally. All right, let's see what else we've got. Ben has an interesting question about how nodes work. Could a node's ability to ban a peer potentially be used as a mechanism to control the network by a set of actors? What are the requirements for nodes to be banned? Does the system implement an on-chain voting mechanism? Ben, to clarify here, when we say that a node is banned, it's only banned for you, meaning that your node may choose to ban another node. It's a bit like blocking someone on Instagram or Twitter, right? You block them. That means you can't see them anymore. Everybody else can still see them. So your node will implement bans, and these bans are never permanent. They're usually temporary because it is assumed that it might have been a mistake. If your node receives an invalid transaction or an invalid block or an invalid protocol use by another node, something that is not according to the consensus rules or violates the protocol in some way, your node will stop talking to that node and disconnect from it. And that's called a peer ban. Your node blocked them, and you stopped talking to them because they were one of your 8 peers that you were talking to. So your node is selective as to who it talks to. This ensures that if a node connects to the Bitcoin network and it starts lying about transactions and blocks, every time it tries to lie, every node that it talks to will ban them. And so they'll end up cut off from the network, because every time they try to tell a lie, they'll get a 12-hour or 24-hour, 36-hour block from that node that they just tried to lie to. And that node will no longer talk to them, but there's no mechanism by which you can say, hey, everybody ban Ben. And for exactly the reason you imagine, Ben, because such a rule could be used to abuse the network, to fragment the network, and to cause denial of service attacks. So there's no mechanism to ban a node for everyone. Every node makes its own decisions without trusting anybody else. That is a fundamental principle of the network. And that extends to whether or not you should listen to another node. Your own node decides, and when it decides, it only applies that decision to itself. It doesn't tell anybody else, because why would anybody else trust you? You say they lied, but if they haven't lied to them yet, it doesn't matter. All right, there's a couple of questions about mining. All right, let's take some. I see a couple of questions in the forums, but I think some of the questions from the live session are more relevant to the topics we're discussing this week, so I can answer some of the follow-ups to those. Nicholas asks, transactions are stored in a hash tree before entering in a block, like a Merkle tree. No, Nicholas. They're stored in a database on your own node called the mempool when they're waiting to enter the blockchain. Your node collects unconfirmed transactions and put them in this waiting queue, or bucket if you like, which is called the mempool, which holds all of the transactions your node knows are yet to be confirmed and are waiting for confirmation. It's a waiting room. Every node has its own waiting room for transaction, and it keeps those in there. But before transactions are in a block, that's the only place where they're waiting. They're waiting in the mempool of each node in the waiting room. They don't go in a Merkle tree until they are in a block. So a block contains the Merkle root of the transactions in it. A block doesn't really contain transactions. The reason it doesn't contain transactions is because it only contains the Merkle root. The transactions are sent with it and marked with it, but it only contains the Merkle root. You can prove that a transaction is in a block by calculating that Merkle root, but the Merkle root is the only thing that's stored in the block header, the root of that Merkle hash tree. And that's really the purpose of the Merkle tree, is to summarize all of the transactions in a block down to one single hash that can be stored in the header of the block. Marcelo asks, can you sum up how the most simple node is set up? You run a small computer, Raspberry Pi, or maybe a small PC. You can even do it on your laptop or your desktop if you want, but it's nice to have a dedicated PC that stays on all the time. I use an Atom PC or a Celeron Mini PC. These are often used as media centers. They're little PCs about this big. No screen, no keyboard, no fans, fanless computers. They cost about $100 to buy. You install an operating system. Most people who do this will get the Bitcoin software and the operating system downloaded as an image that can be booted and installed directly onto this PC. So that's the easiest way to do it, to download the entire operating system and Bitcoin software in a single image. And there are various packages that do that for you. Raspberry is for Raspberry Pi specifically. Umbrel is one that works on both Raspberry Pis and PC, x86 processors. There's MyNode, which works on PCs. And all of these you can download. Essentially, it's an ISO image. You can boot, you can write that to a USB stick, you can boot from that USB stick. It will install everything onto the hard drive of your mini PC, and then you will have a bootable operating system, usually Linux, and the Bitcoin software running on there, and it will manage all of the updates and refreshes and all of that stuff for you. Aaron asks, how does my node select peers to talk to? And the answer is your node will first, when it doesn't know anyone on the Bitcoin network, will connect to a set of DNS entries called the seeds, from which it will download a list of possible nodes. So there are a dozen people around the world who run DNS seeds for Bitcoin, where they keep a list of nodes to connect to. You connect to those nodes and you ask them what other nodes they know about. They'll return a random list to you. You will then connect to those nodes up to 8 in order to establish as peers. And then if they're good peers, they have the correct version of the software, they have the latest blockchain, they don't tell lies to you, you'll keep them. And your node will gradually remember every peer that it hears about, and it will create an enormous list. Once it's done this process of booting once, it will then have a database of thousands of peers. And next time it will select from that list, the peer list as it's known, its own database, and connect directly to those nodes to see if they're still running. And that way, not everybody connects to the same nodes, not everybody seeds from the same nodes. The node selection process relatively random, with some safeguards there so that you can't easily hijack that process. All right, and that's all the time we had for questions today. Thank you very much. I'll see you next week for session 4 of the massive open online course for the University of Nicosia's master's degree in digital currencies. I'm Andreas Antonopoulos. I've been your teacher for this course. Remember to ask your questions in the forums and then attend the live so you can ask follow-up questions in the chat to get the most value from this course. Thank you so much for listening. See you soon.